All right, folks, we're back with video 5 for Unit 1. We're going to talk about what it means to be continuous, or rather, what makes a function discontinuous in today's lesson. So, you should know how to, again, verify if something is continuous or find the values where it is continuous. And then we're also going to talk about something called the intermediate value theorem, which you should have talked about last year, but I'll briefly reiterate that value. And we're going to use that to show that certain values have to exist for our function. Okay, so first let's remind ourselves what types of discontinuities that we deal with. The first one, you might have referred to this in the past as a hole in the graph. It's technically called a point discontinuity. And the definition of that is of a hole or a point discontinuity is let's take a look at the limits. As I approach from the left and the right, my limit does exist because I have the same value for y. But when I actually plug in this x value, which they're calling c, that is not the same. Like as you can see here, I have the actual value much more above what my limit is on either side. So in this case, the limit exists, but it's not a continuous graph. So we can have a limit exist, but not be continuous. And that's the scenario, this hole in the graph or this point discontinuity. Second type of discontinuity we're going to look at is this idea of an infinite discontinuity. Most of you would think of this as being part of a vertical asymptote scenario. And this is basically the limit as, if you look at the limit as x approaches c, really I should say the limit as x approaches c from either side. So I could either say from the positive side or the limit as x approaches c from the negative side. Those two things either approach positive or negative infinity. When that scenario happens, you have an infinite discontinuity. It's discontinuous the entire time. There is no point that actually exists on that C value, and we call that an infinite discontinuity. It is also a vertical asymptote. For the last type of discontinuity that we're going to discuss, you can notice that the limit as I approach from the left and the limit as I approach from the right are two different values. They're not the same as each other. We call this a jump discontinuity because there's a break or a jump in our graph. This is probably the most easiest to see happen algebraically, and maybe the one that you're the most familiar with. So we've got three types of discontinuity: point, infinite, and jump. So, if those are our types of discontinuity, then what is the definition of being continuous? So, these are the three parts of the definition. And when I ask you to prove if something is continuous at a value, you're going to have to show me each of the three parts. In some of my rapid learner classes, I actually have them list them and number them so that they explain all of those. That might be helpful for you too, if that's a helpful way for you to keep yourself organized. Okay, so to be continuous, you actually have to have a value at x equals c. So you have to actually be able to plug in the value you want to look at. The limit as you approach c has to exist. So you actually have to have a limit on both sides. That's the same. And that limit has to be the same thing you get as when you plug in c. So graphically, let's just take a quick look at what that would look like. So let's say that this is my c value. So this first part basically just says you have to have a point on the graph when you plug in C. So you can't have just a hole. So I'm just going to go ahead and put a point for C. The second part says that the limit as you approach C has to exist. So like if I brought in my graph from this side and I brought in my graph from this side, they have to approach the same Y value. And then that third part says that when you plug in C, which is this point, and that limit has to be equal. So what I was just kind of drawing there has to be true. So you have to approach the same thing from either side. That same thing has to be the same thing you get when you plug in C, and obviously C has to exist. So you're going to see some problems in the problem set where I ask you, why is this discontinuous? What doesn't hold of our three-part definition? And so you're going to maybe talk to me about the limit. Maybe the limit on either side isn't the same thing you get when you plug in C or something along those lines. Okay, so let's look at our first example. We've got a piecewise function. We want to know, is it continuous at x equals 3? Let's take a look. Okay, so this graph is going to look like this rational function for everything but 3. And that kind of makes sense because if you think about it, if I plugged in a 3, I end up with a 0 over 0 situation, or it's undefined at 3, and there's a hole in the graph because you can cancel out the x minus 3's and so on and so forth. But what this is saying that is that everywhere else except 3, it's going to look like this graph. So we might as well simplify this graph down and kind of see what happens. So if I were to factor this, I end up with x minus 3 times x plus 3 over x minus 3, which basically means that except for 3, this graph is always going to just look like x plus 3. Okay, so if I graphed that, I could plug in maybe 0, for example, because 0 is something that's not 3. If I plug in 0, I get 3. If I plug in 1, I get 4, and so on and so forth. When I plug in 3, technically, if I plugged in a 3 here, I would get a 6, but remember, I'm not allowed to be 3 there, so I'm going to put a hole, but I'm going to put it at 6 because that's what it would have been approaching. And then I could plug in some points on the other side and so on and so forth. So anytime besides when it's 3, my graph looks like this line. Now, what does actually happen at 3? Well, this part talks to me about that. It says when x is actually 3, I get out 2. So I would have a little point here. That's at 2. Now, is my function continuous at that? Well, according to the definition of being continuous, your graph has to have a limit as you approach 3, which it does. It approaches 6. You have to be able to plug in 2, which I can. I get 3. But here's our problem. These two things, the limit and the actual value, are not the same. So clearly this is not continuous. If I had to tell what type of discontinuity it is, we can tell that this is a point discontinuity. So I'll just label that here. Okay. So then sometimes I want to know, well, when is my function continuous? Because we're going to want to study functions later, but them being continuous is going to be a very important part to what we study. So we need to know when it's continuous. So let's look at this guy. If one of the things that can cause issues with continuity, of course, is vertical asymptotes or zeros of the denominator, or holes, right? So we're going to look for any possible problem that a function could create. And in the scenario that I have in example 2, I have x's on the bottom, which means there is a possibility for creating some problems. So let's see if there are any. I'm going to go ahead and take my equation. I'm going to set it equal to 0 and see if there are any values for which x would be, this whole bottom would become a 0. So let's solve it. So I get x squared equals 4. I get x equals, careful, plus or minus 2. So what does that mean? That means that my function is continuous for all values except this. So some people say like x can be any real number except x cannot be plus or minus 2. Most of our work and on the AP exam, you're going to see this written as negative infinity to negative 2. I'm going to leave out negative 2. Then I'm going to go from negative 2 until 2, which I need to leave out. Whoops. And then off to infinity. So technically you could say it either way. This is the way that the AP exam likes to do it. Okay, let's take a look at example 3. I still want to find the values of x where the function is continuous. So I want to look for anything that would cause my function to have problems. Now, the obvious first problem is I can't have a denominator be 0. So again, this one I could do probably without solving, but x cannot be 8. So I do not want to have x be 8. But this graph also has an issue with the top, which if you haven't already noticed from the previous problem sets, you can't take the square root of a negative, right? So we need whatever is under that square root to come out greater than or equal to 0, because it needs to be something that's not negative. So I can solve this inequality. So x has to be greater than or equal to 7/3. So these two things have to work together. So x has to be anything, or x can be anything bigger than or equal to 7/3, but it also still can't be 8. So how do we write that? We end up with a domain this is also known as the domain, that would say, okay, I can be everything greater than or equal to 7/3. So 7/3 is the smallest I can go, and I can actually be 7/3. Normally, I would say to infinity, but am not allowed to be 8. So I'm going to stop and leave 8 out, and we're done. Okay, let's look at our next example. Same deal. We're trying to find when our graph is continuous. The first thing that I notice is that I've definitely got some values in the denominator that involve x, so that's something I'm going to have to look at. The tricky thing that sometimes slips students up is that the numerator can be 0. So the fact that I have x minus 7, 7 is fine. That's not going to cause an issue. I'm allowed to have 0 on top. My only issues are the bottom. So I'm going to look at the zeros of the bottom. Since they're factored separately, I can look at the zeros separately. So this one's easy. This one, x is not allowed to be -3. Again, I can set up an equation and solve for that, but that was pretty easy. This guy, we've just dealt with square roots, so we know that our square roots have to be positive, which means x squared minus 25 should be greater than or equal to 0. But there's an issue. This square root is in the denominator, which means it's actually not allowed to be equal to 0. So whenever you have a square root in the denominator, you need to make sure you go back and say that that just has to be greater than 0. You can't actually be 0. So to solve this, I have to kind of think back to algebra 2 a little bit. When we did this in algebra 2, we would let our inequality, because that's the problem here, we would let our inequality become an inequality and solve. So if I solved this as if it were an equal sign, I get plus or minus 5. And then to figure out when my inequality is true, I would have graphed those zeros, if you will, on my number line, -5 and 5. And because I'm not allowed to actually be 0, these should be open circles. Okay, then I would test intervals. Remember doing this? So I would plug in a number. Like if I plug in 0 for x, let's see what we get. 0 squared minus 25 is -25. Is that true? Is that greater than 0? No. -25 is something that's less. So none of these values in here are going to work. Then we could try something on this interval, like 6. If I plug in 6, I get 36 minus 25. Is that value bigger than 0? Yes. So all of this section would work, and then I can tell you all of this section also works. So there's my answers that work. You can also solve this graphically. So if I graph x squared minus 25, first of all, I know the zeros are 5 and -5, so I could graph those. And my parabola opens up because it's positive x squared, so I'm going to have a graph that looks something like this, roughly. And if I want to know when my function is greater than 0, remember that's my output, so we're talking about y equals 0. When is this graph greater than that line y equals 0? Here and here, which guess what? Are when it's less than -5 and greater than 5. You just have to make sure that you check to see whether you should include these values or not. Okay, so now I need to make sure that these restrictions relate to those. So if I were to just write this, I would have negative infinity to -5, not including -5, and then from 5 onward. And then I would go to check that this isn't an issue. So x can be -3. Well, that's actually fine here because I've already restricted, -3 is already not a part of this. So this is good to go. Let's just say this was -8. This were x can't be -8, then I'd have to change this part so that it would exclude -8. But for now, we're good. Okay, our last little example uses something called the intermediate value theorem, and you should have talked about this last year, but the intermediate value theorem is basically this. If I show you graphically, I think you'll have an easier time. It says if you plug in two different values for x, and I'm gonna just give some arbitrary y values. So maybe when I plug it in here, I get a 2, and then maybe I plug in b, I get like 11, okay? If my graph is continuous, and that is important, continuous meaning that it doesn't matter how large or small it gets, but it doesn't have any places where there's vertical asymptotes or holes or whatever. Then that means when I plug in A, if I get 2, and when I plug in B, which is bigger than A, I get 11, then that means that every single number from 2 to 11 on the y-axis has to be met to get you from A to B. It could even be a straight line, guys. It would still cover all those y values. So if I want you to prove that there's a value that gets me 50, I need to show that there's a value that's below 50 and above 50. So I'm going to do 0. So if I plug in 0, I get 6. That's not too bad. And then you can pick any other number you want. I'm going to plug in 2. And when I plug in 2, I end up with 56. because this function's continuous, which it is, it's a polynomial, there's no issues. I know that it has, if from 0 to 2, it goes from being 6 to 56, then along the way somewhere it had to have been 50. So this right here, by intermediate value theorem, shows there must be a place where the output is 50. All right, good luck with the problem sets. See you in class.